been talking about static systems. You can see this?
Yes, sir.
Yes, sir. Okay. So we looked at two problems in static systems. One is this Rankine earth pressure, which is basically just supposing you just have a pile of granular material, then under gravity, what will be the stress distribution? And we also looked at another problem with a stress distribution in a rectangular bin. Excuse me. So in the last class, I showed you that we can actually use lamps and then just pour particles in a rectangular box like this and then calculate the stresses using lamps. Of course, each time you calculate the stress, each time you do a configuration like this, there will be different sort of patterns and all that you will get. Here I wanted to show you that the stresses are usually transmitted along certain particle chains, and in between you may have very low stresses. So this is the nature of these systems. But as you do many of these type of configurations and you average them, then you can get very nice results. And here I'm showing you the different stress components XX, ZZ and XZ. I showed this last time also, versus the height. So this is the base at the bottom of the container, and then as you go up, this is how the stress varies. So the stress is 0 at the free surface as we had assumed, and it increases linearly with depth. Over here, the red line is sigma ZZ, which is in the gravity direction, and the black line is the stress in the horizontal direction. And sigma XZ, which is the green line, is the shear stress, and it is 0. So what this means is that sigma XX and sigma ZZ are the principal normal stresses, and sigma ZZ is larger than sigma XX. So this is sigma max and this is sigma min, and this corresponds to an active state, active Rankine state. If you calculate K as just sigma ZZ by sigma XX, you get, because they are straight lines, you can easily find out what is the ratio. It turns out to be 1.3, and that gives an angle of internal friction to be 7.5 degrees. So this is one thing that I showed you last time. And then we were looking at this problem, that supposing it's the same as before, X, Y, whatever. So you have your normal stress in the X direction, normal stress in the Y direction. And then, we showed that if you have incipient failure everywhere, that is sigma max by sigma min is equal to K, then that gives you an expression for sigma YY like this in terms of the angle of internal friction, beta, sigma XX and sigma XY. So now you have three unknowns, sigma XX, sigma XY and sigma YY, and you have three equations. So we can always get a solution to this. And the boundary conditions we saw were that the stresses all are 0 at the free surface. Also, because this is a line of symmetry, then both of these gradients are 0 with respect to y. And also the shear stress, because it's positive in one part and negative in the other, at the center line the shear stress is 0. So this is at y equal to 0, and at y equal to w, you have a frictional wall, which gives us that the shear stress is the coefficient of wall friction times the normal stress acting on the wall. So this is our problem that we want to solve. And we saw that if there is no friction on the walls, then we get sigma xy equal to 0, and then the solution is just the Rankine solution as before. If we do a cross-sectional average and we make the approximation that sigma yy at the wall is approximately equal to sigma k times sigma average xx, then we get a very simple equation, and this can easily be integrated to give us this. And what we saw is that in this equation, as x becomes very large, this term goes off to 0, and so you have a limiting value of the normal stress, which is given by this. And if you look at the graph, this is our Rankine solution, straight line, but this one, it kind of saturates and you cannot exceed this stress, the maximum value. And then why does this happen? We also did some analysis of that. And the reason is that even though the weight is acting down, the weight is carried by the wall friction, which is given by this. So wall friction holds up the particles, leading to a limiting value of the normal stress in the x direction. Okay, so this is the physical explanation for that we saw. And you can do an exact solution also for this problem. There is one method is using the method of characteristics, which is given in this paper, but it's equally easy to do a numerical solution, and I'm going to put the write-up for that on Moodle, so you can see that how to easily integrate the equations that we derived earlier. And this actually shows sigma xx divided by some characteristic stress. So this is a dimensionless quantity. This shows how this sigma xx varies with y. This is essentially, we want to see how this sigma xx, how does it vary in the cross section? How does this vary in the y direction? And the reason that we wanted to show this is because of this approximation that we have made, that instead of writing k times sigma xx at y equal to w, we have written it as the average value of sigma xx. So now if you look at the exact solution, you can see that sigma xx varies very slightly with y. Each line is for a particular value of x. X is the distance from the free surface in the direction of gravity. So this is near the free surface. Then as you go deeper and deeper, the stress becomes higher and higher, but then this is x by w equal to 2, and when you reach x by w equal to 10, you can see all the lines are all falling on each other because the thing has saturated. But the key thing I wanted to show you is that essentially there's not much variation at a particular value of x. The variation of sigma xx with y is not much. Hence that approximation that we made is quite okay. And in this graph, I'm showing the actual value of sigma xx versus x. And this dashed line is the cross-sectionally average solution. And these two other lines with the points, they show the exact solution at y equal to 0, which is the center line, and y equal to w, which is the wall. And you can see that they are reasonably close, so the cross-sectionally average solution is quite a good approximation. So with that, I want to stop talking about statics, and then let's see how do we look at slow flows. And there I'll talk about two different methods of looking at slow flows. One is the Moore-Coulomb and the critical state theory. And then we'll apply both of these to a very simple problem, which is flow in a wedge-shaped hopper. Okay. So, any questions so far? Okay. So now let's go on to today's lecture. Some new things we can talk about. And today is now we are going on and on, so we have reached which lecture have we reached now? So this is according to me. Now we are on lecture 17. Okay. So today's date is 2nd of September. And so let me first share the screen. So it is 2/9/21 and we are on lecture 17. So as I said, I wanted to talk about slow flows. But before I go, I'll just make a small digression. And that is, how do you calculate stresses? So, as I said I think in an earlier lecture, you might remember that you can easily calculate the stresses. And I showed you an example also in this class where we calculated all the stresses in the system, where we have got a container and we put all the particles in, and we could actually calculate the stress at every point. So how do we do that? So I wanted to just explain to you the theory behind it. It's a simple idea. So what we do know from all the simulations and so forth is that we know the forces between the particles. Now suppose we want to calculate the stress. See, whenever we talk about stress, we have to say something about which surface. So supposing in our system we want to calculate the stress on this surface S. Okay. And so what we can imagine is that if this unit vector is n, then the only contributions to the stress acting on this surface is essentially those particles, because the only stress between particles is when they are touching. So the only stress that can happen is if we have particles which essentially are spanning this surface. So one particle is on one side of the surface, the other particle is on the other side of the surface, and there is a force that is acting one particle on the other. And let's say that force we know how to calculate. That is through either the Hertz model or the Hooke model or whatever it is, but it will be a vector and we'll call that force is Fij. So now if we know all the forces acting across this surface, the sum of those forces will be Fij. But how do I know? I mean, if there are two particles that are over here, There may be an Fij over there also, but they are not going to contribute to the stress on the surface S. They have to be such that one particle is on one side of the surface and the other particle is on the other side of the surface. So the total force that is acting on the surface which I'm going to call F total, this is just going to be equal to the sum over all the contacts. So there may be many contacts within the volume of particles touching each other, like we saw in the just a little while back in that example. And you're summing over all the contacts and you want to add the force Fij. But this is not wrong. This thing is wrong, because while this pair is contributing to the total force, this one is not. So how do I make sure that this is the right thing? And the way we do it is we multiply this by a probability, I'll call it as Pij, where Pij, this is the probability that Xij crosses the surface. Where of course we know from earlier things that Xij is nothing but Xi minus Xj. So it's that vector. So that vector joining the centers of the two particles, it should cross the surface. So this is the probability. And what is Pij equal to? Well, there's a very simple expression for Pij. Okay. So if supposing this length is L, then the length of, or the projection of Xij in the direction of n is just going to be n dot Xij. So this is a component of the vector Xij in the direction n. It's a scalar quantity. So essentially for this, if we look at it, the particular length I'm talking about is this. So this is, I'll try and draw it neatly so that it doesn't confuse everything. So this n dot Xij is this red line. And what I can do is I can simply divide this length divided by the total length. That will give me the probability that this red line is crossing the surface instead of being anywhere else. So this is the simple result. And this essentially, once we know Pij, then we get our total force that is acting across the surface is just equal to sigma over all the contacts of Fij into, I'm going to write this as Xij dot n. Okay, because the order of taking dot product doesn't matter between two vectors. So this is what it is, and this is just divided by L. So this is the total force that is acting on that surface. And we know that, so this is the force. So what is the stress? The stress vector on the surface, this is nothing but F total divided by the area, which we will put as L squared. So I should write stress, I put in brackets vector. And what is the stress vector on this surface? Well, that is nothing but the stress tensor dotted with n. We know that if you want to calculate what is the force per unit area on a surface with unit normal n, then that is nothing but F dotted with n. So this is what is the stress vector. So this implies that sigma dot n is equal to F total. Now we can replace that. So you get 1 by L cubed sigma over all the contacts of Fij Xij dot n. Okay, so now you can see there's a dot n in both places. And so if I remove the normal vector, then you get the general expression what is used, that the stress tensor is nothing but, if we look at any volume, it's just the sum of all the forces Fij times the distance between the centers of the force, like this. And so this is how LAMPS calculates the, in fact, what LAMPS, when you want to calculate the stress in LAMPS, what LAMPS will give you is this. You'll get just this. And then what you have to do is, let's say you're considering a certain volume, and this is considered per atom. So for each particle you will get this value. So if there are two particles, they just divide it equally between the two. And so you get this value for each particle, and then you add it all up for all the particles in a volume and divide by the volume to get the stress. Okay. So this is what I wanted to explain to you. In fact, instead of L cubed, we can just put it more generally as just the volume. So this was an aside, and so just so that you know how these stresses are calculated when we do computations with particles, so that the stress is simply obtained as the sum of the force times the distance between the force between the particles times the distance between. So both are vectors, so you can see this is nothing but a dyad, which is a tensor. Now let's go on to the next topic, which is slow flows. And as I had briefly mentioned, there are essentially two ways in which we can look at these. One is exactly the same as statics. So this is the same as we use for static systems when the particles are not moving. So you have those same sort of conditions, and in this we will assume that the bulk so we see more Coulomb condition is satisfied everywhere. And bulk density. So these are the two assumptions. is constant. And this gives us quite reasonable approaches and quite reasonable results, and we'll show this. The other approach is, of course, there are many theories, but I'll just tell you about one of them, which is called the critical state theory. Okay, in which changes in bulk density are explicitly changed. Sorry. So the main issue over here is even very small changes in bulk density can make a huge difference in the stress values. So if your bulk density changes even by 1%, you may get a very large change in the normal stresses or shear stresses and so forth. And hence, you need to make some correlation between them. And so if you look at what are the postulates or the assumptions of this theory, then what it says is that one, that the yield criterion is of the form that some function of sigma 1, sigma 2, sigma 3 and rho b is equal to 0. So it's not only the principal stresses but also the density. So all those four are related. The second postulate is what is called the coaxiality condition. Okay. Which says basically that we've calculated the principal axes of the stress tensor. Similarly, we can also calculate the principal axes of the rate of deformation tensor, which is basically the symmetric part of the velocity gradient tensor. So, what it says is that both of these are coaxial. So what it means is that the rate of deformation is maximum wherever the normal stress is maximum. So rate of compression is maximum where the normal stress is maximum. And wherever the normal stress is minimum, you may have an expansion or you have a lower rate of deformation. So this is what it means, that wherever you put more force, there will be more deformation. So they are all lined up. So this is what is the meaning of coaxiality. And then you need one more thing, which is what is called as the flow rule. So, the main point is that you need enough equations to be able to solve the flow problem. And so this is one more set of conditions, and this also relates the rate of strain to the stress. And this flow rule essentially says that we'll explain this in more detail, of course. No need to. Where di are the principal components of the rate of deformation tensor, and sigma I are the principal stresses. Okay, I've said rate of deformation tensor many times, and all of you who have done fluid mechanics know this, but let me just put it down again. So if the velocity gradient tensor is given by gradient of v, where v is the velocity, then the rate of deformation tensor is simply, it's generally designated as d, and that is just gradient of v plus gradient of v transpose divided by 2. So this, you can see from this itself that d transpose is just equal to gradient of v transpose plus gradient of v transpose divided by 2. What happens if I take the transpose of a tensor twice? What will happen? Can someone tell me?
It should yield the same tensor again.
You'll get it back again, because you know you are just interchanging rows and columns. So if you do it twice, you'll get back the original tensor. So this becomes equal to gradient of v transpose plus gradient of v divided by 2, which is equal to d. So what this says is, oh sorry, which is equal to d. This and the first one are identical. So what it means is that d is a symmetric tensor. Okay. So these are the things that we will look at, and really what this theory does is that one is because of the yield function being a function of density, so you can get explicitly the density in the system, and then this essentially tells us something about the rate of strain tensor, and this also tells us about the rate of strain tensor. Now lambda are unknown constants. Uh, which has to be found out from the solution, and G is called the plastic potential. So this is actually a property of the material. So by solving all of these, we will see that, and I'll give you exact examples of each of these functions, that you can actually get the full velocity profile in the system. And when, if G is equal to F, where F is the yield function, then this is called a associated flow rule. That means that the flow rule and the yield function are associated with each other, and we are going to basically use this. So that means we have only one function. This is F is equal to 0, and di is lambda of df by d sigma I. So this is basically our two approaches that we will use. And so in the next class, what I'll do is I'll write down what are the governing equations, and then we'll do examples for both Moore Coulomb and critical state theory. Both of them we will take up in the next class. So I'm going to just rub that out because we haven't done that. Okay, so now I hope you're all ready for the quiz. The quiz is quite simple. Um, you don't have to worry about it. What I want you to do, and I'm going to remain on this for a little while. I want you to just try out and see if you can leave this meeting and join the meeting for your corresponding group. So can you do that? And can you turn on your cameras when you do that?
Sir, which group should I join? Two?
Uh, you know,